Okay, chapter 3, part 2, discussion of relative motion. So we have just discussed the Galilean transformation for different reference frames. And if you want to compare and contrast velocities with different systems moving in different directions, you definitely have to use Galilean transformation. Here is a problem that is a good example of what's going on with that transformation. We got a passenger on the boat, and the boat is moving at a certain rate on a still lake. So lake is just still, and the boat is moving just by itself with respect to the lake. Okay, so boat with respect to the lake, that's what's given. And then a passenger is trying to get to the second level, and the rate for that is 0.6 meters per second. And not only that, but also the stairs have a certain angle with respect to the horizontal axis. So what do you say for this 0.6? It's the velocity for the passenger with respect to the boat. Okay, it was boat with respect to the lake. Now it's the passenger with respect to the boat. Do you see the different reference frames? Right? We have three objects to work with: the lake, the boat, and the passenger. And what we have given here is boat with respect to the lake and the passenger with respect to the boat. And of course, there is a complication of 45 degrees as well that you have to take care of, because velocity is a vector. You can't just add 0.6 and 1.7. You have to do components, as we did in previous vector algebra problems, and take care of both components at the same time. Because remember, time flows the same way for both x and y axis. So the question is, what's the velocity of the passenger with respect to the lake? See, it says water or lake. Well, lake and water means the same thing. So either you want to say water or lake, it's the same thing, lake or water. So let's draw the vectors that we have to work with. Let's see what's given. Let's see what's missing. First of all, it's the boat with respect to the water. That is what's given. Check the diagram. 1.7 meters per second, horizontal motion towards the rightward direction, or you say eastward. This is your first velocity vector, and the subscripts would be B and W, both with respect to water. And then we've got the passenger with respect to the boat. It is 45 degrees with respect to horizontal, and the magnitude is given. So the magnitude of this vector is given, and it's 45 degrees between the orientation of the water and the passenger moving. And as you can already guess, we are to find the vector sum between B and W and P and B. Passenger P with respect to the boat, so PB, and BW, that's what's given. And we're looking for PW. We're looking for passenger with respect to the water, passenger relative to the water. So my Galilean transformation starts with what we need. What do we need? We need passenger with respect to the water. When you say the lake, well, lake is still, anyways, just passenger in the water. That's the resulting vector. And the first subscript P goes for the first spot on my transformation. And the second subscript for what I want takes the last spot. See, we have 4 spots, P, B, B, W. So first, second, third, fourth. So first is taken by first. And the second subscript for what we need goes to the last spot. And what's in between is something that we have to get rid of, specifically between the boat, the water, and the passenger. We don't want the boat. Our final answer should not include the boat itself. So boat takes the second and the third spots for my transformation equation. I can say boat cancels, and you're left with PW, so purple coefficients cancel, and you're left with those black subscripts. That's what we're looking at. Well, should be clear. Once again, you can't just add numbers. Vectors are not scalars. They have this certain ways of addition and subtraction. You have to do that separately for x components and y components. So first of all, you're doing the x component, and well, that's what we're looking for. And what's given is 0.6 as the magnitude, but we only want the x component, only this part. And this side is adjacent. In this right triangle, you can think about a right triangle. And I'm only looking at the side that is adjacent to 45. If it's adjacent, it's a cosine function. So I'm taking the hypotenuse and multiplying it by the cosine of the given angle. I understand that 45 degrees is a very special angle. Sine and cosine will give you the same value of rad 2/2. It doesn't matter. I still want to point out it is a cosine. Please do not replace it with sine for any reason. You have to show the cosine because it's adjacent for that specific reference angle that is given. Plus BWX. BWX. You can see that BW is just horizontal. So onto X, it is as is. No sine cosine, and it's a positive value because it has the same direction as X axis. So just as is, 1.7 added to the X component of the passenger with respect to the boat gives you 2 point something. I'm going to keep some more sig figs because it's intermediate calculation. Do not round here. And the same equation applies to the y components for the velocity vector. This is what I'm looking for. And it's the y component for this dark brownish vector. You want the y component. Remember, there is a right triangle. And we just found the adjacent side for x component. Now for y component, you are looking at the side that is opposite to 45 degrees. And if it's opposite, it is a sine function. It's also positive because it's clearly pointing upward as your positive direction for y-axis. So it's positive, and it's a sine function now. And what do you say for BW? BW is all horizontal. So what's the component of BW onto y-axis? See how this vector is perpendicular to y-axis. And the rule is every time something is perpendicular to some vector is perpendicular to a certain axis, that component on that axis is 0. That's why you have 0 for the y component for that vector, because it's perpendicular to y-axis. And then you do the math, you end up with this value. Once again, it's a little more sig figs because it's not the final answer. And now we have two components for the vector that we're looking for. So what do you do with those components? You do the classic distance formula or the Pythagorean theorem. You have 2 point something units in the x direction, 2 point something units in the x direction, and you have 0.4 units in the y direction. So your parallelogram method introduces you to this right triangle where you know the adjacent side and opposite side. This is also 0.4. So 0.4, 2.1, square this plus square that, take the radical out of the total, and you're going to get the magnitude of the vector that we're looking for. So my passenger is going 2.2 meters per second with respect to water, okay? See, it was passenger with respect to the boat, and it's 0.6. But if you want to consider what's going on with respect to the still water, it's going to be more because the boat travels pretty fast. And see how you can just add up 1.7 to 0.6, you're going to get what, 2.3, right? It's 2.3, but the actual amount is 2.2. And it's not just a rounding error of some sort. No, it is just a different value. So you can't add vectors as scalars. You have to follow the Galilean transformation if you have more than one system for calculating vectors. And don't forget that vectors have two things, magnitude and direction. You just figured out the magnitude. It's only worth half credit because you haven't specified direction yet. And in order to get the direction, you need to show the sketch and you have to choose a reference angle. This time, I want to choose the angle with respect to horizontal axis as my reference angle alpha. And if I know two components, I can use inverse tangent function to figure out the arctangent of this angle. Arctangent, opposite over adjacent, opposite 0.4 over adjacent 2.1 gives you 11 degrees. It is time for you to grab your calculators and see for yourself how your calculator should show you the same answer. And if it doesn't show you that, make sure you switch from radians mode to degrees mode. Most common mistake is your calculator is set to radians, and if you want degrees, then you have to switch to degrees. So magnitude is 2.2, and direction is 11 degrees. Once again, see how it is different from the given 45 degrees with respect to the boat. Because one thing is the boat, one reference frame is the boat, but if you want the lake to be the reference frame, then everything changes. You are left with a different answer, a very different answer. Okay, any questions and comments? Put them in the chat. Moving on to the last problem from the chapter. So we got raindrops that make a certain angle theta with the vertical when you look at them through the window. I'm pretty sure you've seen those this effect when you go through rain on a moving car or a train, maybe airplane, I don't know. You will see how rain looks not vertical, but at a certain angle. And the speed of the train is given. And the question is, what's the speed of the raindrops in the reference frame on the Earth? So right away, we have three things to consider. We got the Earth, the ground. We got the train moving with respect to Earth in a certain direction. And then we have water. We have rain that is also moving. It's falling, but the point is it's moving. So rain falls, train goes, and Earth is sitting still. So three different objects to work with. Okay, right away, a common mistake. Oh yeah, this is the setup that you might end up with, but that would be an incorrect setup. Let's see what's wrong with this setup. Train relative to Earth, it's given. Yeah, makes sense. This is a good vector to show. See, you have velocity of a train with respect to Earth, with respect to the ground. So going that way, definitely a good vector to draw. There's nothing wrong with this vector. Then we got rain relative to Earth, which is unknown. So for unknown, we don't know. And then the green vector. Oh, this is not train relative to rain. Which angle is theta? Yeah, see how theta is something different, right? You have an angle with respect to the vertical. And in here, there is no such theta. You can't really put any theta here. So let's take a look at the proper. So this is totally incorrect. You can't consider train relative to the rain. It's just, yeah, because we need rain relative to the train. That's what's given. Oh, okay. So this is your mistake on subscripts. It's not train relative to rain, it's rain relative to train. So remember, A with respect to B is not the same as B with respect to A. And you can fix the order of subscripts by introducing a negative to it. So what we need is rain relative to Earth. That's the question. The question is, what's the speed of the rain in the reference frame of Earth? So it's R E. R E. Rain with respect to Earth. What do we know for Galilean transformation? We know that R must take the first spot, and E must take the last spot. So we have 4 spots, 1, 2, 3, 4. So R goes to the first spot, E goes to the last spot. And what we don't want takes the second and the third spots and kind of cancels each other. So what we don't want is the train, right? Remember, we have rain, train, and Earth. If we want rain with respect to Earth, we don't want the train, so train takes the second and the third spot. This is the correct Galilean transformation. And the problem is you got rain relative to train. Rain relative to train. That's a good one. And that's your velocity for the rain. And that's the theta that it's given. right there, rain with respect to train. That's what you see. Sitting on the train, looking at the rain, that's the angle theta that is given. That's the correct vector to work with. And there is still train relative with respect to Earth. That's given. See how I said this vector is a good one. So we're going to use this vector here as it's given. There's no problem between those two. And finally, it's rain with respect to Earth that we're looking for. So it's RT plus TE. And the triangular method of adding two vectors tells you to start with the beginning of the first and end of the second. That's the rain relative to Earth. It should be vertical. Unless there's like wind, the rain would just fall vertically, but we're not talking about wind. Wind is not discussed in the problem. So this is the correct vector diagram. This is the correct approach to consider vectors. And now it's just solving for what's given and what's missing. I want to point out that tangent of theta is given. And what is tangent? Tangent is opposite over adjacent. Opposite is the red vector, TE. And adjacent to theta is what we're looking for. So what we're looking for is going to be TE divided by tangent. And that's exactly what we got as a solution. So the given speed of a train with respect to Earth divided by the tangent of the angle that is given will give you the speed of raindrops with respect to Earth. See how funny it is? You are sitting on the train and you see how raindrops are not vertical, but you can tell how fast they go with respect to Earth, not the train, if you use the Galilean transformation correctly. Now, I should admit that this problem is a little advanced. It's a little more challenging than the boat ones, like this boat problem or the one that we had in lectures. On the test, you'll definitely see something simple rather than the rain and train in the Earth. But you can see that this is a universal tool to do all those calculations. And it's not just for velocity vectors. You can use it for any vectors. For motion, that's very useful once you start talking relativity. And, it's very, very helpful towards the end of mechanics. Okay, this is it for classroom discussion. I'm going to pause the recording and we're going to do something else after that.